So all of those condensed structural formulas and Lewis structures we just went through were to show you how condensed structural formulas work, but also to introduce you to new functional groups and remind you how to draw Lewis structures. That was a lot of practice. Here's some more good practice. We'll draw these together, but you really probably want to do some of your own from table 1.5 in your textbook. Do some more practice with these condensed structural formula things. We'll start with this first one where I've got a carbon connected to 3 hydrogens. That carbon connected to a CH2. That carbon connected to a C. And then what? Here's parentheses. A lot of condensed structural formulas have parentheses, and those parentheses can mean various things depending on what's neighboring them. This carbon where I left off needs to make 4 bonds. That means he's got 3 more vacancies. So really, this carbon is connected to a CH3, another CH3, and the CH that comes next. This CH is connected to an OH, which is in parentheses. It's getting a little crowded down here. But that CH still has an availability to make a bond. He's connected to the CH3 that is the final CH3. Whew, that got a little bit big, right? That's my framework, but is there anything missing? Oxygen has 2 lone pairs. So if we did our formal rules of totaling up the number of valence electrons, if we then counted right now, we would see that that matches. How do I know without even counting that it matches? Carbon likes to make 4 bonds. They're all making 4 bonds. Oxygen likes to make 2 bonds and have 2 lone pairs. That's happening. Everybody has a full satisfied octet. Everybody has the right number of bonds according to typical bond numbers. It's great. It's good. I like it. What functional group is in this molecule? I hope you're shouting at your screen, alcohol. But it's kind of hard to see that there's an alcohol in there because it gets real jumbly. It gets real big and complicated. In comes skeletal structures. This is the skeletal structure, one of the possible skeletal structures to represent that big giant molecule. How did I get there? Well, I know I've got, I can't count, 5 carbons. I know I've got 5 carbons in a line. That's those 5 that I've numbered, 5 carbons in a line. And those, if I look at those numbered carbons, carbon number 3 has 2 single CH3s connected. That's these. And carbon number 4 has an OH connected to it. That's this. So while you may have originally thought, man, skeletal structures, I don't like them. They're going to be complicated. If I look at that blue jumbled mess on the left and compare it to the purple stuff on the right, that purple structure is much more clear, much more obvious that there's an alcohol in that molecule. I don't have to do quite so much detective work to find it. Yeah? Okay, cool. The next one, I have a CH3. And then comes another parentheses. In these parentheses is CH2. Well, CH2 leaves 2 vacancies for bonds. So apparently all 4 of those CH2s are connected in a sequential chain like this. 1, 2, 3, 4 CH2s are connected. Then comes another CH2. Why did we not put them all together and say there's 5? I don't know. Then comes a CO2. Carbon connected to oxygen and oxygen. Yeah. if we were doing this together in real time, I would make you pull out your textbook and try to find a functional group that has 2 oxygens in it. And you would search and search and search, and you should pause this video and search and search and search, and find that we have 2 main functional groups that have 2 oxygens in them. One is a carboxylic acid, and one is an ester. Well, because what comes next is a carbon group, I know that this thing should be an ester. So I'm going to connect my final CH3 to one of my oxygens. Don't go back and connect the final CH3 to the carbon. It's connected to one of the oxygens. How do I know that? Because I've looked at my functional groups and I know esters look like that in general, except an ester has to have a carbon doubly bonded to an oxygen, singly bonded to an oxygen, doubly bonded, singly bonded, and a carbon on the other side. So this is an ester functional group. Carbon doubly bonded to an oxygen, singly bonded to an oxygen with an R group over there, and an R group over here. That's an ester. So this molecule has an ester. Is this a completely finished Lewis structure? Not until I put in all my lone pairs around my oxygens. Then it is. It's a really long chain of carbons, and then an ester. You guessed it. We're going to draw the skeletal structure next. That's 7 carbons in a row, then an oxygen, then another carbon. So let's zigzag that thing. 7 carbons in a row, then an oxygen, then another carbon. Carbon number 7 has a doubly bonded oxygen on it. None of the other carbons have anything special. This bottom thing is my skeletal structure of that molecule. Way easier to see that it's an ester in this skeletal structure, but this one's not too complicated either way. And finally, to my last example on this page, CH3. CH3 2? How does that work? Well, really, this set of parentheses tells me these 2 CH3s are connected to the next thing in the line. So there's a CH that has 2 CH3s connected to it. So this C is that C. CH connected to 2 CH3s, 2 CH3s. And then I continue down the line, and this CH is connected to 2 CH2s. Well, CH2 means a repetition of CH2s. And then comes a CHO, a CHO. We've actually seen a CHO before, and I didn't call it such, but CHO means aldehyde. This condensed structural formula has an aldehyde. That's C, doubly bonded to an O with an H on one side and a carbon group on the other. That is an aldehyde. The skeletal structure of an aldehyde has 1, 2, 3, 4, 5 carbons in a row. 1, 2, 3, 4. That's really bad counting, but I'm leaving it there anyway. 1, 2, 3, 4, 5 carbons in a row. Doubly bonded oxygen on the 5th carbon, and a methyl, a CH3 group on the 2nd carbon. So stick a spike off of that one. There's my skeletal structure, my complete Lewis structure. Ta-da! So we've been talking for a while about skeletal structures. Here are the actual rules in written out form. Each vertex and endpoint is a carbon because carbon is our favorite. Hydrogens on carbons are assumed because they're omitted in the actual skeletal structure. But you need to fill carbon's octet every time. The only way that you wouldn't fill carbon's octet is if there's a formal charge of positive, for real. Hydrogen on heteroatoms. What the heck is heteroatoms? Heteroatoms, anything that's not carbon has to be explicitly drawn. So like this nitrogen has 2 hydrogens, those must be explicitly drawn. Hydrogens on heteroatoms cannot and shall not be assumed. Let's draw out these examples. Let's take these skeletal structures and draw them out explicitly as carbons and hydrogens, full, big Lewis structures. Let's do that together. So in order to draw these, I'm going to keep my same general framework so that I can keep things straight as far as what I've drawn and what I haven't. What I mean by that is carbon, triple bond, carbon, carbon, carbon. I'm keeping things in the same angle, at the same perspective. I'm not trying to make it a straight Lewis structure. Keeping it at the same angle helps me make sure that I've gotten all my carbons included. So there's all my carbon connected stuff. And then I assume enough hydrogen to make carbons make 4 bonds. So this bottom one, that's making 3 already. So 1 hydrogen is assumed there. This carbon is making 4 bonds, no hydrogens included. This carbon is making 3 bonds, 1 hydrogen has to be included. Students then start saying, how do I know where to put that hydrogen? It doesn't matter. I pointed it this direction. You can point it that direction or that direction. This carbon has 4 single bonds, 4 domains of electrons. It's an sp3 hybridized carbon. It's a tetrahedral carbon. We don't care which direction you point it in a Lewis structure. We care that you can, in your mind's eye, visualize that being a tetrahedral carbon. Whew, yeah. Carbon on the end here has 1 bond already, so 3 hydrogens are needed to make him full. Carbon here has 3 bonds, needs 1 hydrogen to make 4. 1 bond needs 3 hydrogens. 2 bonds, 3 bonds, 4th makes a hydrogen. 1 hydrogen, 3 hydrogens. It's not always easy at first glance for students to go from a Lewis structure to a skeletal, but I think most students can go from a skeletal to a Lewis fairly easily. You just got to be able to count to 4 for all the carbons to know how many hydrogens, and you have to know when to add lone pairs. All of the carbons have 4 bonds, so none of them should have lone pairs. How would I know if it should? In order for carbon to have a lone pair, I have to have a formal charge in my skeletal structure. There ain't one, so no lone pairs on my carbons. The next one looks like this. And we need to draw it explicitly showing all atoms and their connectivity and all lone pairs. So I'm going to start with, down here, I know I've got a carbon connected to an oxygen. I'm setting up the same sort of framework that I did for the last example, keeping my stuff in the same orientation as it is in my given example, but I'm just putting carbons in at all of the intersections and endpoints. Done. Then I go back and fill in hydrogens. Carbon needs 3 hydrogens to make it full. Oxygen needs 2 lone pairs to make it full. Carbon needs nothing more. Oxygen needs 2 lone pairs to make it full. Carbon has 4 bonds already. Carbon has 3, he needs 1 more. Carbon has 3, he needs 1 more. Carbon has 4, done. Carbon has 3, he needs 1 more. Carbon has 3, he needs 1 more. Carbon is full. Oxygen needs 2 lone pairs in order to make him complete. Nitrogen needs 1 lone pair in order to make him complete. Woot woot, isn't that great? Skeletal structures. Before we totally finish this off and say, that's enough for today, let's go back and highlight functional groups or talk about functional groups in these molecules. This is what functional group? An alkene, I hope you shouted. This is an alkyne. This one has some functional groups that we have seen, one functional group we have seen, and some that we have not. This is an ester. This is a benzene. We will also call this an aromatic ring. I don't care what you call it at this point in time. We will talk about all of that way later in the class. And this that has a C double bond O with a nitrogen with carbon groups or hydrogen groups, it doesn't exactly matter, is an amide, A-M-I-D-E, amide. Amide is what lots of you will call it. It's an amide to me. There are 3 functional groups in that molecule. You have to recognize functional groups. Okay, that's really enough for now.